The next speaker is Fredrik Korsbäck, and he's from NORDUnet. And he's going to talk about greenfielding a new nationwide backbone. How hard could it be? Welcome.
Thank you. Right, so my name is Fredrik Korsbäck. I'm usually known as my stage name, which is Hugge. Active in the community and usually found around on IRC and other networking type of events. I work for a company called NORDUnet, which I'm only going to have one slide about because this presentation is not actually about NORDUnet. But I think it's important to know where I come from. So NORDUnet is an RNE network. It was mentioned by Puff earlier that we started pretty early, 1989, I believe. And we have a big carrier network all around the globe, and we take care of everything that's related to research and academic stuff for Scandinavia. So usually when we're out in Europe, or US, I talk as NORDUnet, but internally in Scandinavia, I usually represent SUNET, which is the Swedish Research and Education Network. And why I'm here today is that SUNET has built a new network, or it's actually building right now. And I wanted to share some stories and what we actually do. So we need some history first, and we need to speak about the current network, which is about 10 years old. It's actually exactly 10 years old. And we connect the whole Sweden. We have 3 systems, which are called north, east, west. And the whole network is built as a dual hub and spoke. We have a green and a red network, which are completely isolated. They are never allowed to cross each other, and everything should be at least 10 meters apart. So this has been serving us pretty well. It was debated when we built this the first time, because we have a few problems with it from architectural point of view. And that is, so we have no ROADMs in this network, by the way. Everything is point to point. But one of the main problems we had was there's a really long last mile, because the hub in the hub and spoke network is Stockholm. So it's actually in the first iteration of the network was that when people in Kiruna wanted to speak to people in Luleå, they had to go through Stockholm, which is suboptimal. But it was what we could afford at the time, and it has changed slightly. We do have express pods now, especially up for the northern people. But it's still a quite old network. We use Sienna Core Stream in the current one, which has gone end of life for many years ago. It's a bit stable platform, but it's pretty old. And also we have a few, like, I mean, these optical stuff, they're so bad, right? I mean, the management of these optical gears it's Telnet and other weird protocols like TL1. So it's horrible to manage. So we needed something new, and also due to legislation, actually, we needed to buy new stuff because everything was end of life in terms of tenders. So we needed to put up new tenders. So we wanted to build something new, and of course we wanted to build something that was better, something that was cheaper, and something that was more scalable. So we had a pretty good group of people that helped us with this. Some of this are in this room. Peter has been a good help, for example. And we wanted to make something new, and also to actually, because I mean, we're a research network, so we wanted to do something new that's not been done before. So we went out with a tender that we would need a new, because this is dark fiber, everything is dark fiber. So we went out with a new tender for a new optical network, and we started with the dark fiber, because it's really hard to know what we need to do unless we know what we have to build upon. And in this case, I'll build upon dark fiber. So we wanted a few things out of this. First, we need a better topology in general. We can't have a hub and spoke again, because we did have some problems where we actually had failures in both the red and the green network at the same time, which cut essentially off half the country from the internet. Because it should be noted that all of our customers are single-homed behind us. So if we have a problem, then they lose everything. So we had it happen a few times, which we didn't want again. And that usually happened because, I mean, there wasn't supposed to be any cross-sections in terms of fiber, but that was not the actual case. So there's been a few incidents where both the red and the green network have been sharing the same pipe, or whatever you want to call it, the same trench. So we wanted that, and also we wanted a new topology. So we're building some sort of a star, small circles in Sweden. It's not actually seen here on this picture because this is actually from the KMC data, but we're going to go in a little bit on that later on, exactly how it looks like. And we also want to support for special applications, for example, just to transfer frequency or light. That doesn't necessarily doesn't need to be like a protocol on it. It just has to be light, which can be relevant for a few scientific purposes. And of course, we wanted everything to be 100 gig, because this network is going to last for a long time, so it needs to be at least 100 gig, and also supports whatever comes in the future. Because when we do these tenders and when we buy stuff, we buy it to be in the long game. So for fibers, we have bought this dark fiber on 10 years that we also can extend that to 15 years. So we wanted to buy the correct thing, not something that would just work for the next 3 years. We needed something that works for the long game. And as well as coming to that later, but in terms of optical gear, we want the optical network to last for a pretty long time. Because we don't believe that the optical network should be intelligent in this case. All right, and we also have least capacity to Visby. So there's actually a university at Visby, but it's a very small one. So we're actually relying on least capacity to Visby, which we're probably fine with for another 10 years. Anyway, so the fiber plant currently is from Tele2. They won the tender. And it's of course not only Tele2, it's a lot of vendors involved in this, because to be able to build a national network in Sweden, you probably need to involve somewhere around 70 to 100 subcontractors. Because every city in Sweden has their own little stadsnät, as we call them. So there's the municipality that has built some type of fiber plant in the city. You could be the power company, the local power company, or the municipality in its whole, or just a city that has agreed to do a city network, like Stokab in Stockholm, for example. So the fiber we ended up with is that we have a mix of new and old fibers, and we also was very keen on having the O3R measurements, because we need to know exactly how the fiber performs to be able to buy the correct equipment, and also to be able to plan ahead on what's coming next. So it was a must-have in the tender that we need O3R attenuation data delivered on every single fiber that we have in terms of the core network. And that also that we need proper KMZ data, and KMZ data is the map data that we can put into Google Earth or any other mapping program. This is to make sure that we don't end up like we did with the last network, that we actually have a lot of intersections that cross each other, or fiber that goes in the same trench. Because this can't happen in a new network either. Nothing is allowed to cross, nothing is allowed to be in the same trench. And if there are KMZ data, we at least have something to point on that, all right, if the KMZ data is not true, then we have a problem. We have both about 8,000 kilometers of fiber throughout Sweden. This is not including the access fiber, which is much harder to buy, or well, not harder to buy, but it's harder to get all these requirements fulfilled. So the access fiber, which usually goes from the city pop out to universities or to the governmental institution or the research facility or whatever it is that student is allowed to connect, is almost always from a city network. And they usually don't have KMZ data. They usually don't have O3R measurements. They usually don't have any kind of data on how much splices there are, or if the fiber has been repaired, where it has been repaired, and if the quality of that repair is actually up to what it should be. So we couldn't put that requirement in, because then we wouldn't end up with any network. So they're a bit lighter in terms of requirements, but so far we have been able to get this working decently. All right, so here's actually more information on that. And for the backbone network, we have that we only allow one patch the first 20 kilometers, and that is because we don't want that much reflection due to Raman amplifiers, which I'm also going to talk about a bit later, why we need them and what they're good for. We also do measurement of the water peak. It's characteristics in some fiber that you have that a certain wavelength gets a lot of attenuation, and that wavelength is also used by Raman amplifiers. So if you have uneven attenuation in fiber on a specific wavelength, the Raman amplifiers does not perform that well. We also require OTDR measurement both on short pulse and long pulse, and I have pictures of why we require this a little bit later. And yeah, I think you can read the rest. I think this is. We thought that this should be well enough to get a real good optical backbone going. Turns out that now that we actually know a bit more about how like 400 gigabit will look like in 1 terabit DWDM, we probably should have even harder requirements that we need less attenuation, less reflection, we need better fiber, and better measurements. But this is what we have right now, and it's working out decently. We also require that every single connector in this network is photographed with a microscope and sent in, and to also pass that test. Because we had so much problems when building networks, for example, for NORDUnet, that people are so bad at connecting fibers that they get so much dirt in that you can destroy connectors, or you get so bad performance out of connectors that it's virtually unusable. So to guard against this, Tele2 in this case has to provide pictures of every single connector in the network, and that they have passed the test. And for the ones that work at Tele2 in this room, you probably know that this wasn't that funny to do, because there's a lot of connectors. There's thousands of pictures in our folders regarding these pictures. But that makes sure that the vendor actually does this, because there's no way to escape from that. All right. We also had another thing. So why I put a new way of building networks in is that we didn't really want to put money into the optical vendors' pockets here, or rather, we want to spend as little money as possible. So we tried to do something with IP over DWDM. And to understand what this is, we first need to understand what classical DWDM is. So the picture above is there's 2 routers, the purple boxes. They, on 100 gig, they typically have like a SR10 interface or an LR4 interface of any type of form factor. Then you plug this in with a local connection to a DWDM transponder, which is in an optical chassis of some sort, which makes this into OTN signal, a coherent OTN signal, O2.4, to transport it long haul. This, of course, as you can see, it requires more interfaces than the picture below, where we do the OTN framing directly in the router. And we started this 1.5 years ago, or actually started way before that, but actually started to do elaborations and do stuff with this. So it was quite early in the process. There wasn't really anyone that had anything. Cisco, Juniper, Huawei, and Alcatel, or Nokia nowadays, had some stuff in the labs, and Deutsche Telekom was experimenting with this, but there wasn't anything deployed really. So we tried it out, and we actually got it to work. There's been a lot of tech cases back and forth, but it's starting to look like something. And this is of course has many features. First, we need to buy a lot less interfaces because we do the framing of OTN directly in the router, and also that we get a bit agility. I think is the marketing term, that the router can decide itself what type of wavelength it wants. And also I put in the red there, I put in gridless. This is because we don't use a MUX in this network. So we just use splitter and combiner instead of a classical grid, which has like channel 54, 55, 56, 57, and it needs to be physically plugged into the correct port. In this case, we use splitters and combiners so that the interface can be any wavelength, essentially. All right. I'm putting in this first nationwide network. Might not be true, but it's at least one of the first one that does this on 100 gig. This was done a little bit on 10 gig, but didn't take off that much, at least from what I can see. We had tried it out in SOONET actually with 10 gig, but didn't really work that good. So to be able to build this, we had Juniper, or rather they won the tender on this, because we put up a tender and everyone answered, and it was Juniper that came out on top. A few things to note here is there's this thing about FEC. There is a few people in this room that cares a lot about this. I also do. So we have this called SD-FEC, with the soft decision FEC, which is what you can call the secret sauce. If you have two boxes on either side of the network and they going to speak SD-FEC with each other, it needs to be the same SD-FEC. And so if you have a Cisco on one side and a Juniper on each side, they probably don't have interoperable SD-FEC. So you need the same equipment on both sides to be able to speak to each other. It could be debated that SD-FEC is a little bit better in terms of performance. It usually is. It goes a little bit further. There's also SD-FEC that does 200 gig in DWDM signal. But you can't speak to anyone else except yourself or similar equipment in that case. That's why we have the thing called high gain FEC or staircase FEC or cortina FEC or I guess a famous kid has many names. So that is, if we put it easy, it's an open source version of FEC. It's publicly available. Anyone can download the spec, exactly how it looks like, and how you should build high gain FEC. So we had that as a requirement because we don't know if Juniper is going to win the next tender, but we might still have some Juniper equipment left. So if Cisco comes and win, there needs to be a way these devices can be interoperable with each other. And if high gain FEC is available, then we can make sure that every vendor can speak to each other. There's also the GFEC, which is a short distance FEC, which doesn't really work in our use case, but it's still there. And this is implemented in a card that you will see like this. And it has the thing called CFP2 ACO. So ACO stands for analog coherent, which means that this FEC stuff is not done on the actual transceiver, but it's done on the card. And that is why there is two big cooling things in the back of the card, because one of them is actually the SD-FEC DSP, and the other one is the high gain FEC DSP. But the actual transceiver is analog in the essence that it doesn't do any of the FEC stuff, but it does the optical stuff, of course. And it has -20 input power, and it's chromatic dispersion tolerance, and all that stuff that usually comes from the that you speak about when speaking about optical backbone. So the framing is actually done on the actual card and not on a transceiver. So in the future, we will probably see that this is not how people build it. They will probably try to integrate the DSPs directly into the CFP, of course, because the thing is with this card is it needs to look exactly like this. It's not pluggable per se. It needs to be exactly like that, which is a bit unflexible. But if in the future we get CFPs with everything here in this card integrated into the transceiver, then we can plug and play essentially everywhere. And if it also supports high gain FEC, you can plug and play it for real everywhere, on every vendor. This is a quite big thing, right? Because a company like Infineon or Ciena, they take all their pride and put it in this SD-FEC, that our SD-FEC is the best secret sauce on the planet, much better than everyone else's secret sauce. It's usually essentially the same, but they take a lot of pride in that, and of course it's nowhere near compatible. But we're actually seeing a bit of a trend, like if we look at what Broadcom did for the switching market, this is essentially also happening for the optical market, where we have vendors which only sells these DSPs to whoever wants to buy it. A company called Acacia, for example, does this. And anyone is allowed to buy their DSPs and put into their equipment, which is kind of handy, that we try to break this market a little bit. All right, anyway, enough about that. So the network itself, if we put it out on an omnigraphical sheet, it looks like this. So all the blue boxes here are ROADMs, and all the green lines are the actual optical lines, which we run N by 100 gig in. So we have a few cities, and I guess the special thing with a company with SUNET is that we also need capacity to example Kiruna, because there's an international space station in Kiruna. And also in Narvik, where we help out the Norwegian research network with capacity in case if Norway gets cut in half, which has happened a few times actually. So they can actually take a route through Sweden if need be. We also have small cities like a village like Onsala, where we have the telescope. So what we do here as well is, I'm going to skip to here, is at every university, we're going to put 2 routers. And to be able to save money here, we only put 1 core router in every city. Soon it is very much about being redundant, that it should never go down. It should be a top-of-the-line redundant network. But we couldn't really afford to put two core routers in every city because that's a lot of routers. So we only put 1 core router into the city, and we put the whole optical layer there. And out of the university, we're using Juniper MX480 as CPE devices. And one of the MX480s is taking the best possible fiber we could get in the city, and just use gray LR4 interfaces. So that fiber needs to be below 8 dB in attenuation, and it just speaks locally to the router at the core. But the other router speaks with or have a coherent interface that goes to the next city, which should be not on that picture, but it actually goes to the neighboring city. So it doesn't actually connect to the local city. So for example, in Örebro University has 2 routers. One is connected locally to the city. The other router is connected to Västerås through the optical system to be able to buy half as many core routers as we would have needed otherwise. Which is kind of handy. This is working really well, actually, because the coherent interfaces we have the longest we have run these is about 2,000 kilometers. So far, we don't have a good stretch that goes further than that, but it should be. But 2,000 kilometers is quite enough for all of our use cases in this case. And also, yeah, this is the shopping list. What's also interesting here that we put these gridless filters out of the university. This is so that if we get another application at the university that needs capacity, it's extremely easy for us to add more 100 gigs. This would probably happen down in Lund. We have the ESS, which is going to require a lot of capacity because it's a joint project between Sweden and Denmark where they put the actual scientific instrument in Sweden and the compute is in Denmark, which means that we're going to need to shoot a lot of capacity between Lund and Copenhagen. So we can do it very easy with these splitters and combiners. All right, shopping list is as follows. So Juniper won the tender for the routers. So we have MX480s at the university, we have 960 at the core POPs, and in the big cities we have MX2010 or 2020. And why we need these big routers is because these cards that I just showed you are extremely undense. It's just 100 gig per card, which means that we subscribe the routers immensely. Not because we wanted to, but that is because that is how the card looks like. So that for example, in Stockholm, we fill that with 13 slots on day 1. So we really hope that these cards get much denser over time, which they are. But we're running these first-gen cards. And in the optical, we have ADVA with the FSP 3000, and ILAs is as well ADVA on the same platform. It should be noted here that we buy 0 transponders from ADVA, which is quite unique in an optical network like this. Because, of course, the optical vendors want to sell transponders, because transponders is what you make money on. But we bought them from Juniper instead. And, as I said, with high-gain FEC, we can replace any router here with a Cisco or Huawei or anything that speaks high-gain FEC, and we're good to go. All right, some pictures from deployment. This project actually started rolling out this January. So January, we got the first sites and the first fibers that we were actually allowed in. So we have been rolling out a little bit ourselves, all the like trial and error we did ourselves, and after that we used Eltel as a partner to actually do the actual rollout and install electricity. As you can see there, there's an MX2020, it's a DC powered, so that's a lot of cables. And we were driving around in our little Volvo truck and actually rolling these out. Yes, some pictures on how it could look like. This is the network in itself, how it will look like with all nodes, with all amplifiers. It's some kind of amoeba, whatever you want to call it. But one other interesting thing that we also did was that we wanted to optimize the network for as good OSNR as possible. That is optical signal to noise ratio. And this is because we need that this network lives for a long time. So we wanted to do it right directly in the beginning. So we're going to use something called Raman amplifiers on a lot of stretches. Actually, more stretches than we needed to, because we want this to be plug ready for 400 gig and also 1 terabit. And we use Raman amplifiers, and should be noted here that Raman amplifiers are extremely sensitive to reflection. That is why we already in the tender process, we had this thing with photographs on every connector, because if you have dirt in a connector, you will get reflection, and these Raman amplifiers won't even start. So if you bought a Raman amplifier for $10,000, you kind of want it to work. I mean, there's no need to have it just sit and idle. So you want all of them to actually work. This is not done. From our side, we still have outstanding issues on about 13 locations, and we started this in January. And in the beginning, I think we had 72 outstanding issues, so we have 13 left. And this is usually to bad fiber, or bad connectors, bad ODFs, and bad cleaning of fiber. And the few things we have left now, we probably need whole site rebuilds to be able to get down the amount of patches in the beginning. So that's going to probably take, to get all our Raman amplifiers to work, that's probably going to be done somewhere in like July next year, is the projection. So if anyone else is building a big national network and you want Raman amplifiers, which you probably would, then please allow for a lot of time to actually make sure that all of them starts. So that's still going to be a challenge. And we get a bit difference in gain. The best ones we have about 15 dB, which is really good gain, and 9 dB we can live with, but we probably want a little bit more gain. So if you want to read something very confusing, read up on this Raman amplifier works on Wikipedia. It's magic, but they're pretty cool. All right, so if we take a look at a OTDR measurement for Raman section, so this is how it could look like. This is usually what the vendors provide you when you need, I want to buy a dark fiber between Västerås and Stockholm. This is usually what you get. Doesn't really tell you that much. Looks pretty okay. It looks like any decent fiber, but this is with a long pulse. This measured the whole distance. But as I said earlier in the fiber tender, we had that, all right, we also want a short pulse on a short distance to make sure that we see only the first path of the network. And this can look like this. So all of these that goes up, these are actually reflection. So we don't lose that much attenuation, as you can see, but we have a lot of reflection. And this is a stretch where the Raman amplifier didn't start at all. It just shut down immediately because it does self-sensing, like, all right, can this stretch work for me? Can I actually put light in this fiber? And it does a few tests, and then comes back with, no, I get too much reflection, so it will just shut down and be totally worthless. And this is not good. So this is probably APC connectors, all of this. And this is typically a site where we would like to see only 1 or 2 of these, and then we could get the Raman to work. So this went back to the drawing table, of course, to reduce the amount of patches and connectors and splices to make this better. So this is the picture to the left is probably one of the best connectors we got, which meant that it's meant as a joke. So, but it's actually true. So this is probably one of the best connectors we have, because usually out in the forest on all these substations, people they don't put in the dust caps. They don't care about being clean around the fibers. So this is usually what it ends up with. And this could be the difference between a Raman not starting or a Raman starting, or it could be a difference between a few dB on the actual fiber, or it could be nothing. But to be really sure, we wanted every connector to look like the one to the right, which should clear the IEC testing phase. There is a lot of local Eltel and these optical people that is outside in the countryside that hates us, because I mean they couldn't take lunch at 10:30 anymore. They actually needed to work, so they don't like us. But it's because of this reason, because they did it wrong 10 years ago. So now they're eating that up again. All right, so this is another OTDR measurement, and as you can see, we're doing OTDR measurement here with 4 different wavelengths, and the the picture above, there is one wavelength that performs much worse than the others, and that is because of this water peak thing, which is actually I can't say that I'm an expert in this field, but it was something at the time when when people did this type of fiber that had that is a peak in attenuation for a certain wavelength. And the problem is here that the Harman amplifiers uses one of these wavelengths to actually excite the lighting inside the fiber. So this will probably also result in that we get pretty poor performance. And this is hard to solve because you don't want to change aerial fiber that sits on top of a power line. It's actually impossible to change it. So to be able to work around this, you either need to ingest another site in the middle so that you can use only EDFA amplifiers, regular amplifiers, or you try to change pair to another pair, which hopefully is a little bit better. So we have about 2 or 3 of these left, where we have the one above, which seems really hard to solve. So we will need to ingest another site in the middle to actually get the full performance out. This picture below is actually on a good fiber in terms of at least that all 4 wavelengths perform equally well. All right, a typical site somewhere in the forest looks like this. So this is an amplifier site, I believe. This is just south of Uppsala, where we did initial testing. It's a little hut somewhere in, usually very close to the substations or the power lines, because as I said before, almost all of our fiber is in power lines. And there is usually some kind of backup power everywhere. Hopefully that also works. That is also maybe tested at least yearly. There is some requirements in the contracts as well that this needs to be tested and actually filled with fuel and all that stuff. So we had a few incidents where this wasn't the case. So because the thing, what we do, me and my colleague thinks it's pretty funny to do unannounced tests of everything to make sure that processes works, that the NOC, in this case for Tele2, actually does what they're supposed to do, acts on alarms and try to actually trip the burglary alarm and see if the cops comes, but they don't come. So, so this is quite an interesting challenge, and then hopefully things get solved by doing these kind of tests, because we want this to actually work, of course. So this is a very typical site. This is a typical POP site, because we have these big racks on the sites where we only have amplifiers. We're well enough with just a little telco rack. That is fine. But on the real POP sites where we put MX960 or bigger, we need real racks. But the POP sites is usually one of these small huts. And if you ever work with the Juniper MX960, the power supplies is in the back, and they're pretty big. So you actually need pretty good room behind them to actually be able to work with them. So the solution, which I really like, is kind of a MacGyver solution, is that we put all the racks on wheels to be able to slide it back and forth. So this is actually a guy here in Stockholm that made all this for Tele2. It's just a local blacksmith that did this. And it's quite genius solution actually, because it's tip safe, because you have a little thing in the bottom there that actually keeps the rack from tipping over. And to solve the cabling in the top, we have a cable chain to be able to pull the rack back and forth. And this works surprisingly well. We loaded 2 old guys into the rack and could slide it back and forth just with the fingers perfectly. And this means in any given day, the rack will be put directly against the wall, and if we need to reach behind it, we just pull the rack out and change power supplies, pull the cables, whatever it is, and still you can fit into this little POP site. To be able to build this network, to be said that SOONET only consists of 3 people in terms of engineering, so we didn't have much time or much manpower to do stuff. So, and all of these routers, I mean, they're really big routers, right? And we can't get 30 MX960 into the office to pre-configure them. And the good thing is that Tele2 is also a cell phone provider, so they had some 4G SIM cards that we could take or buy, I guess. Actually, I guess we pay for them, but so what we did is that we bought a console server that does 4G. So we deployed 4G console servers on every site that sits in a directly. So these SIM cards is actually doesn't actually go on the internet. These are programmed to hit the VPN directly, which terminates in our office. So all these boxes call home to our office, and this makes that we can provision that all the boxes get sent out from the box straight up, no configuration, nothing. And Eltel, which is the installation partner in this project, just need to plug in the serial cable into the correct slot in the router, as well as the optical equipment, so that we can take over from the office. They don't need to log into the routers, which is a great thing, because these people, they're usually electricians. They're not console people. They might not even have a computer. So since we didn't want to buy 30 laptops for field engineers, we thought this was a good solution. We actually tried at first with Eltel sitting and like set interface loopback and then an IP address. That took forever. So this was actually faster, so that we can make sure. So we can use 4G, make the boxes reachable, and then we take it from there, which is quite handy. And also, if the site dies or if the fiber dies, we can still log in through 4G and make sure that the site is alive and do troubleshooting. So all the DWDM nodes come pre-built from factory, in this case by ADVA. So all internal fibers are connected, scoped, and make sure that everything is perfectly nice and clean, just as we want it. And the site installation partner, Eltel, just do shelf interconnect. So they just essentially plug the line fiber in to the ADVA equipment and then plug the client into the Juniper router. So they need to do minimal amount of plugging cables in. Routers and DWDM nodes come completely unconfigured directly from the box in the little plastic bag, and we have a permanent 3G and 4G connection, and then we do it configuration with RS-232, and also that one thing to be noted here that which is kind of bad actually is that the Juniper routers can't actually boot straight off the bat with these DWDM cards, because the routing engines has too old image, so they can't boot any of the DWDM cards before upgraded. So what we did is we uploaded through 4G. We don't have a data cap, by the way, so we uploaded a 2.5 gig Junos image to every one of these console servers, so we could just SCP them locally over to the Junos box. So we could upgrade it and then get the DWDM cards to work. Right. So the solution, as I said before, looks very much like this. We have two university routers. One is local to the city, and one goes directly on the DWDM system and connects to the other city. And everything, as I said here, is 100 gig coherent. And in the future, we can easily swap that out for something faster, if need be. And one thing we also do is that at the universities, they can actually, we actually give it away for free, to give a logical system in these routers to the campus, which is shown in this picture. But we can actually speak about this first. So the university usually, or the campus networking in this case, they're usually pretty good at switching, not so much routing. And they might not even want to buy a router. So what we do is that we can slice these routers in small pieces so that they get their own router from us. It doesn't cost anything for us, and we have pretty decent trust in our customer base. So we slice the routers up in different logical systems. So we keep the SUNET logical system by ourselves to do management and upgrades, and also if you want to terminate something that's not a university at the university. For example, every state museum is connected through SUNET, which is usually like a gig connection or even less. So we can terminate them into the logical system using the museum's IP addresses and all that stuff, while the university gets another logical system where they can run their actual internal routing inside, which is quite handy. Because it could be said here that every university, in an essence, owns SUNET. So so we have a good deal of trust going on here. But of course, a few universities want the classical ISP handoff, that we do eBGP from the CP devices to whatever they have. All universities has their own AS number usually. Usually pretty low as well, because we were quite early at university networking. So there's a few that still likes to do this, that has their own routers and likes to do it their own way. But this is getting more and more and more traction with this type of solution that we actually run them for them, or they run their own router inside our router. So I guess if this was a sales slide, this would be called an NFV or something. All right. So back to monitoring then and management. So since this is actually this is show interface from the DWDM card. As you can see, there is a lot of more knobs and small different types of things you can actually look at, because this is quite important numbers for everything in terms of optical networking. For example, one of the things that we had big problems with in the beginning was this little thing down here, which says total power and signal power. And if we go back to see that this is actually a gridless network, so we get all light from all transponders at the same time. We can use the term optical hub. So every single interface, because a coherent interface is tunable both in the receiving end and the sending end, which means that the total power is not the same thing as receive power on the actual wavelength. So in the beginning of this card, we could only see total power, which was super confusing because we just saw that we had light, but not that we had the correct wavelength. And this was before this was actually implemented. It was a broken network. You couldn't know anything about it. So they had to implement it, and it was quite quick because they realized it quite soon as well. Oh yeah, this can't work if we don't see signal power. Then we have the specific OTN kind of stuff, like carrier frequency offset, then Q2 factors and SNR, which no one cares about in this room. But it's very important that this actually is as good as real optical equipment from Siena or Infinera or whoever of these legacy companies we speak about. No one joking? No. But also that we can see FEC in terms of corrected errors. How hard is the FEC actually working, so that we make sure that we're not on the edge of how much the FEC can do. We need to be well within limits of getting bit errors. In terms of management, that's something we care deeply about, and that the waves are provisioned with GMPLS inside the ADVA. I'm not sure this is actually the future, but this is what we have right now, at least. So we can actually build optical channels inside the ADVA equipment with GMPLS. We want, in the future, that the ADVA NMS actually speaks directly to the Juniper transponders, just as if there was an ADVA transponder, to do the tuning of output power and also the monitoring of the optical values. We also, of course, want NetConf in the ADVA NMS. This is committed to 2017, and if this doesn't happen in 2017, we will send all boxes back to ADVA in a container and say that they're broken. And as both you will hear from Christian, you heard from Kalle before, so we actually use NSO from Cisco, which was before called NCS from TLF, to control all configuration. So now we're 95% of the configuration in every single Juniper device is owned by NSO. It's not owned by a human. And we probably want that to be 100%. The thing that is currently not owned by the central orchestration is customer-specific things like MTU sizes, because that always differs if the customer has a Cisco Nexus or a Cisco 6500 or something else. These MTU sizes always differs, and other very specific things. But it would be great to get 100%, but 95% is probably good enough. This also means that when we deploy new routers, we deploy new routers in 45 seconds. We just need to define what they are, and then the orchestration inside NSO, which is the protocol nowadays, takes care of the rest. So we've spent a lot of time actually building with this. Because, I mean, we're three people, and none of us actually works 100% on this, essentially. We also have the other network to take care of, NORDUnet, so we need to make this very streamlined, because we don't want to hire more people. And we, of course, believe that young models and NetConf is the name of the game of the future if this is supposed to work. Juniper is, as we have heard before, pretty good at it. Adva, not so much. And it's not actually not Adva, it's every optical vendor. I would like to see an optical vendor step up here and say that, yeah, we also believe that this is the name of the game. We don't want any more TL1 terminals, which is impossible to even write anything in. So again, I'm not sure if it was Job Snyder's who said it, but it was from a nanog that API is the new CLI, and that is definitely the truth, and we also believe in it. All right, I'm not sure how I am on time. I hope there's some questions here, and I would advise you to also go in and read the blog, which is there. It's actually my blog, but there's another one which is also very good, but that's in Swedish. But I write in English. We think that, like, we want this to be like an open source kind of thing. That since we build this stuff with government money, it's your money. So we want to give back. So we're trying to be as open as we possibly can with this. To everything that we build, we say exactly how we build it. And we're working right now to actually publish router configurations on GitHub, so everyone can just download our configurations, and hopefully you found something wrong with it, because then you can tell me to fix it, and then I didn't need to work. I just need to fix. So that's perfect. And also, if you want to steal anything, that's perfectly fine. It's kind of the point here. Yeah, I think that's about what I got for now. Questions, please. You want the mic, maybe?
Wait. You said that you had an old network and then the new network. Are there any paths that are the same, so you can compare the difference, for instance, in the OSNR using these Raman amplifiers and such things?
We do have a few which we think is in the same path, because the problem is we don't have the KMC data on the old network, so we don't actually know where the old network is. We just know the endpoints, and a few of these endpoints are the same. So we believe that, yeah, sure, we're probably on the same stretch here, but we're not actually sure.
So have you seen any large differences in the OSNR? Are they much better with the new solution then?
Well, since we forced them to be better, of course. But since the old network is 10 gig only, it's not as sensitive to this kind of stuff. I mean, 10 gig DWDM runs on barbed wire, essentially. So, but 100 gig coherent does not, and especially not 400 gig coherent. So no, we haven't done any good measurements like in between the network, because we don't really care about the old network. Everything is going to be teared down by January. Peter. Give him a mic.
Okay, so as okay, nothing is my fault, but the old network has 17.2 dB Stockholm Luleå, and the new one is almost 26 dB OSNR, and for
worst case, yeah.
Yeah, so for 600 gig, you need 26 dB kind of, or 25.5 dB OSNR to run at 50 gigahertz channels.
Yes.
Then the water peak comes from when you're manufacturing the fiber, basically the climate in the room where you have that machine where you actually put gases inside the pipe before you collapse it. It depends on the climate in that room, and if you had too much humidity, it basically went into the glass, right? So this is humidity from the manufacturing site, and they learned that so many years ago, and they cleaned up. They basically dried out the air there.
Yeah. It's I mean, we have it on a few places. We actually expected it to be on more places. But it's most of these water peak fibers, as we call them, is in the middle of because we have three. I don't want to go back to the first slide, but we have three paths that go from south to north of Sweden. It's the middle one that goes where no one lives. If you go like from Falun and just put a ruler up to Kiruna, it's in that inlands banan, whatever we call it. If you follow that one, we have a lot of really old fiber. Water peak stuff. Hopefully we can build around it. I think it was a question in the back somewhere. Oh, Christian, hello. How many engineers does it require to?
I need the audio. Okay, thank you.
Nope. Take Håkan's mic instead.
Is this on? Okay.
Yeah.
Yeah, Christian Larsen, Deutsche Telekom again. I'll start out with a comment. So on the Interop 100G,
Yes.
I think we have a lot to thank to Peter, who's been doing a lot of those things. I'd also like to kind of say that in our lab, we've done a lot of testing on these things, and it's just this summer actually that we did the last couple of tests between Huawei and Juniper on not just beta hardware, but also on things you can order. So these days you have interop on 100G coherent DWDM between the 4 major vendors, so Cisco, Juniper, Nokia, and Huawei. Second, the question. So you mentioned early on here, if you had known about 400G, kind of the requirements on the optical plant for that, you needed more stringent requirements. Well, so on the optical. Or could you buy that? I mean, a lot of the fiber, I'm kind of familiar with a few of these paths where they come from. A lot of the fiber is old, right?
Yeah.
Is there enough fiber in Sweden where you could actually go out and buy something of higher quality that would kind of match up with the footprint that you want? Right. Or is it new fiber?
So I think this is actually mostly Peter's ideas here, is that the OSNR value that we had in the tender was probably a bit too generous. We should probably put that stricter OSNR. And I mean, you can get this on a lot of ways, right? I mean, you can put the sites closer, so you can have more amplifiers on the stretch and get better OSNR. So I mean, so we're not completely cooked in that. We just need more sites, I guess, because it's hard to get new fiber unless someone actually goes and build new fibers. And of course, that will be the best, that people build more fiber and that they build with good fiber and actually do the right thing here, actually make this good and not have shitty connectors and shitty splices and everything around that. So it would be great if we get new blood in the fiber community in Sweden.
Right. So for the Raman in between, I suppose.
Yeah. We need closer sites. Peter Löttberg again.
So I'm Peter, I can't keep my mouth shut. So
yes, good.
This is actually something that was a very abrupt awakening when you start counting and start looking at this. So what SUNET has is basically an EDFA Raman combination, which basically does backward Raman and does forward EDFA. And it has pretty nice noise figures, but it's limited to C-band because the EDFA is C-band only, right? So if you want to optimize the use of the fiber, you have to get rid of the Raman, have to get rid of the EDFA or do very complicated thing to do LNC bands. That's too complicated to get rid of it. So if you want to optimize the use of your fiber, you have to do Raman forwards and backwards.
Right.
So now, but there is when we started working on the 1T standard and the 1.6T standard, it became obvious that there's this guy called Shannon. Okay, there is just so much energy you can put down in the silica fiber. All the fibers we have in the ground are kind of variations of the same thing. They're not that very different, right? So you can probably put like 35 terabits or so using if you optimize your optics, you clean your connectors, do all of that, you can get about 35 terabit on a silica fiber, and then you're hitting the channel limit, and you can't go past that. It's a hard wall. So putting new fiber in right now is kind of an interesting movie because you know what the upper limit is, what you can do. And we are trying to now see I'm actually trying to build an optimal network just to see what it does. But think about that for a second. Okay, so we get to 35 terabit or so on the existing fiber, then that's it. Then you have to go 2 fibers, 4 fibers, 8 fibers, 16 fibers. So if your traffic grows exponentially, you have a linear technology to match it, i.e. more fiber. So then you can figure out what to do. So, but if this network was built for 15 years, you're okay, right? But next time you have to put something else there. And as I know, there is only something called hollow fiber, and it has a completely different characteristics. It doesn't have the nonlinear effect that makes Raman work, so you can't do Raman. But that's only 10 dB better. So we don't really know what to do next.
Yeah, so you just need to invent something new, Peter.
Yeah, but right now we are kind of stuck, right? So it's just sort of you can do twice as good as SUNET does, but that's it. That's the end of the road because your modulation, you're basically hitting Mr. Shannon. And there's nothing we can do to get rid of them because of the non-linearities in the fiber. I've been talking too long again.
Yeah, also that. Yeah, but it's a good point from Peter there. This becomes more and more advanced as the years goes by, and we'll see when we actually need to start doing things from the ground up again. We kind of felt that we did it this time, that we wanted to build something from the ground up and not just duct tape network together with a mix of least capacity and just be that, all right, we're good enough for 3 years, then we don't need to worry about it. But I mean, we did a tender for fiber for 15 years, at least possibility to do 15 years. So we need to make sure that this actually becomes good already from the beginning. And since this is a green field, that we don't use anything from the old network, we actually had one good chance to do this, and that's now. And it's already passed because we already have customers live in this network, so we can't do that much magic anymore. So we're trying to solve just the last few things, and then we should be good to go. But please follow the build on the blog. I hope you can learn something from it. So we're always open to discussion. Our office is always open for people coming in, and if they want to know something, we gladly tell it. And I'm way over time, so I think we should say thank you.
One more quick question. How close was the router? Here?
Oh,
How close is the router to the wall? I was thinking airflow.
Sorry?
The rear of the MX960,
Yeah.
how close is it to the wall when you pushed in the rack?
It's like 15 centimeters.
Okay, so
something like that. So we have airflow, but not more than that. Peter Lötberg again.
As just a joke, right? So when I used to work, we had sites that were in earthquake areas, and you had to tie everything down so it couldn't move. What happens if you have an earthquake? Would you meet the router out on the street?
Yeah, I guess so. I'm not sure how the earthquakes are in Åmål, but I guess we could have that problem. Then we need to strap them down, I guess. All right. Thank you all. I will be joining on the drinks and everything, so.